Hello again. Welcome to another Stat 510 video. In this video, we're going to talk about random variables. Said another way, we're going to very quickly talk about some key definitions and theorems from Chapter 2 of Wasserman's All of Statistics. I'm going to continue like I did in last video, just freehanding everything, having no sort of like definitions or anything pre-written on the quote-unquote board here. Maybe drop some feedback in Piazza about how you feel about that. I think it makes it easier to follow, but I could speed things along. But at the end of the day, we all know what book this material is coming from. You should probably be reading it, and every single word of it is spelled out here. This is more of a visual compliment to like my voice chatting with you about this. So I don't know. We're testing things out. This will be more important when we get into the heart of the course and introduce new material. But for now, we're sort of just testing things. I've never taught a math course online before, so I'm looking for some feedback there. But anyway, let's jump into it. Let's talk about random variables. I'll see you at the end of the video. Nope, that was wrong. That's better. Okay. So, we're talking about random variables. So, first thing we need to do is define a random variable. So, before we even define it, random variables are so confusing because they contain the word variable in them, which, when we get into working with them, it kind of acts like a variable, but by definition, it's not. So what is a random variable? So a random variable which sometimes we'll just denote as RV, is a mapping. So a random variable, if you think of it as a function that goes from the sample space of a random experiment to a real number. So for some little omega in the potential sample space, if we apply the function x to it, we get a real number as the outcome. So the canonical example of this, and again, I'm not going to go through a lot of examples today, but just one. So the canonical example would be something like flip 2 coins, right? And so first I'll say, well, what are the possible outcomes of that? Well, you could get a heads and then another heads. You could get a heads and then a tail. You could get a tail, then a heads, and then a tail, and then another tail, right? I mean, I'm guessing we've all seen this before, right? So those are the possible, it's a little omega, outcomes. So if I define a random variable x, let's say x is the number of heads observed when flipping 2 coins. So if I apply that function, what do we get? So this should be 2. Here we're verifying if I know how to count. 2, 1, 1, and 0. Okay, so we have now mapped from sample space to the real numbers. So this again is the sample space. This we might call the range of the random variable. I'll often call 0, 1, and 2 the possible values of the random variable. Okay. We could go a step further here and say, what are the probabilities of these events? So I'm going to sort of use some notation without defining it yet, although you've probably seen it before. And let's assume that the coin is fair. So now you notice that in terms of the random variable, there's two different sample space events that equate to a random variable value of 1, and they both have a probability of 1/4. So we could make, we could sort of simplify this table down to be just about the random variable then, and it would look something like this. Right. So, so this row here is a really compact way to say the probability that we flip 2 coins and within those 2 flips, exactly one of them comes up heads is 1/2. So in a mathematical statistics class like this, we're almost always going to live over here in this world where we just directly talk about possible values of the random variable and their associated probability. The sample space is technically always lurking in the background, but it'll be pretty rare that we actually go back and directly talk about the sample space. We'll almost always sort of live at more the level of abstraction of a random variable. This is a note to myself. We need to define this weird thing about how we have a capital X and a little x, but more on that in a bit. No, let's talk about it right now. So this is one of the more confusing things about random variables. So capital X is a random variable. A little x is a potential value. So the little x is a placeholder for, in this case, either 0, 1, or 2. Rather confusing. A legitimate question is, well, why not just use a different letter altogether, like, say, a little k, to which you can't see me right now, but I'm shrugging my shoulders and saying, I didn't develop this notation, someone before me did, and now we're stuck with it. So here we are. Okay. The next thing we need to define is the cumulative distribution function. I'm not even going to attempt to write that down because I will not spell at least one of those words correctly. That is, we want the CDF for cumulative distribution function. So this is a function, we'll call it capital X, and I'm going to give it a subscript. That's also a capital X. That's a little x. So just to be clear here, this is big. This is small. So this is a random variable. This is a random variable. This is a potential value of the random variable. So this will go from the real numbers to the interval 0 to 1. So in other words, one way to think of what the CDF does is that it maps from potential values of the random variable to numbers between 0 and 1. And you might have already guessed that's because we're dealing with probabilities now. So the definition of this function, beyond just the mapping aspect, is like this. So it's the probability that the random variable takes on some value that is less than or equal to some particular value. Okay. Yeah, I'll against my better judgment draw it for this. I'll redraw that. Okay. So that little coin flipping example that we had earlier. Let me check something real quick. Yeah. So we have this. That's not even remotely correct. Okay, we have 0, 1, and 2. And so we have, what, 1/4, 1/2, and 1/4. Right. Okay. So let's draw some axes here. So I'm going to put 0 here, 1 here, 2 here. This is the x-axis, and on this other axis we'll have the value of the CDF. And so I'm going to need markers at like 0.5, 1, 0.75, and 0.25. Okay, now let's use blue. Okay, so, right. So for any, and again, just a refresher, sorry, the CDF is defined to be the probability that x is less than or equal to some x, right? You'll note that sometimes we write this x here, sometimes we don't. If it's clear that we're talking about the random variable x here, we might just omit it, and you're supposed to know it's there by context. Okay, so suppose little x was something like negative whatever. So what's the probability that x is less than or equal to some negative number? Well, because x only takes values 0, 1, and 2, everywhere over here, the value of the CDF is 0. And then there is a jump. So the probability that x is less than or equal to 0, well, that's exactly 1/4. So like that. Okay. And then let's say, what's the value of the CDF when x is 1/2? Well, so what's the probability that x is less than or equal to 1/2? Well, 0 is less than 1/2, so there's, a 1/4, but that's it. So essentially what's going to happen here is we're going to stay constant here. And then at 1, there's a jump because we add about half. And then until we get to 2, it's the same. And then we jump up to 1. I promise this will be one of the only tedious pictures I draw. Okay, so this is a picture of the CDF for that coin flipping example. So with this in mind, we can list a few properties of the CDF. And this is part of a theorem. It's Theorem 2.8 in the textbook. And it has a bunch of subparts, but essentially it says F is a CDF if a number of conditions are met. So the first condition is what we call the non-decreasing condition, which says that if x1 is less than x2, this implies that the CDF evaluated at x1 must be less than or equal to the CDF evaluated at f of x sub 2. A quick glance at this picture sees that that's true. So we can have these regions where it doesn't increase, but we can't ever have it decrease. So again, that's why we call this the non-decreasing property. Okay, next we have simultaneously two things that we need to be true. The limit as x goes to negative infinity of f of x equals 0, and you may guess the limit as x goes to infinity is 1. Okay. This property has the name that the CDF is normalized. So you might notice that all probabilities have to be between 0 and 1. So the most extreme negative value has to be 0. The most extreme positive value has to be 1 because of that fact about probabilities and the previous non-decreasing fact that we just laid down. Okay. Lastly, there's one more property which we're not going to sort of belabor, but it says that the CDF is right continuous, meaning that the CDF evaluated at x is equal to the limit as y goes to x for y greater than x is, of f of y is equal, ignore whatever just came out of my mouth, and what is written down here is true. And this is called the right continuous property. So effectively meaning that if you go the right direction here, the limit exists and is equal to the CDF, whereas it's not necessarily true the other way because of these gaps, depending on which direction you're coming from. But we're not going to belabor this point. Okay, so that's a little bit about the CDF. We're not going to quiz you on these exact properties, but it gives you some intuition about how CDFs work. Okay. New definition. So we talked about the CDF first because I can define it without having to get into the difference between discrete random variables and continuous random variables, but now we will introduce that notion. So the random variable x is discrete if it takes countably many values. So, for example, if the random variable x takes only a finite number of values, like 0, 1, and 2, which we saw in the example, that would be a discrete random variable. Or if it takes an infinite but countable number of values, say the natural numbers, that would also be a discrete random variable. If this is the case, we can define the probability mass function. Which is often referred to as the PMF for the random variable x. And it's simply some function which we denote with a little f, again, big X to denote that it's for the random variable x, little x to denote input to the function, which is a possible value. It is exactly the probability that the random variable x takes that placeholder value. Okay, so that's exactly what we saw here. So this is essentially the PMF of the random variable x that we defined about the coin flipping example. So we could say this is f of x here. Okay, so with this definition in mind, we could realize that to get, say, the CDF of a random variable, you would add up a bunch of the values of the PMF to get it. Okay. Maybe more interesting than that is continuous random variables. So a random variable x is continuous if we need some function. We're also going to denote with a little f, and again, of big X, such that, let's see, I'll say such that fx of x is greater than or equal to 0 for all x. We also need the integral from negative infinity to infinity of that f of x we just defined to be 1. And lastly, if we have a less than or equal to b, then the probability that a is less than x is less than b is equal to the integral from a to b of that f of x dx. Okay. Probably nothing new to anyone, but that's how continuous random variables are defined. And when this is the case, and I should say that this thing we just defined here, this is the probability density function, otherwise known as the PDF. Okay. And when this is the case, the CDF is related as such. So the CDF of that random variable with PDF little f is integrating the values from negative infinity to some particular value, like such. And also, we could go the other way and say that the PDF is equal to the derivative of the CDF at x, where you can at x where at x where the CDF is differentiable. Okay. All right. Okay. So one sort of important note. Boy, I'm not having a good time with this particular video today. One important note is that when you have a continuous random variable, you have to be careful. Densities are not probabilities, meaning that for a continuous random variable x, the probability that x is equal to some x, no matter what it is 0. And perhaps another surprising fact is that PDFs can be above 1 because, again, they are not probabilities. In particular, if we think about this requirement here, we could define an f of x, let's say, on the interval from, I don't know, 0 to 1/2. So something like this. So if I wanted to say to provide a uniform distribution here, in order for this integrate to 1 condition to be met, the value of the density, if I want it to be uniform like this, so it's like this, I guess I really shouldn't draw those, but this has to be the value 2 then. So the value of the density anywhere between 0 and 1 is 2, which is clearly bigger than 1. So just a note there. But if I were to say, what's the probability that x is equal to 1/4, which would be right here, well, that would be 0. It would not be 2. And the fact that it's 0 is a consequence of this fact here, because if I integrate from 1/4 to 1/4, well, that's 0. Okay. There's the lemma in the book that says a few more issues about dealing with CDFs and continuous random variables and how to calculate some probabilities. I'm just going to highlight 2 of them. So the probability, let's go back to black. The probability that x is greater than x. Sorry, this applies to any CDF. Is 1 minus f of x. And this is just a consequence of the complement rule. Because if I write the definition of the CDF here, we get something like that. And we see that this is the complement of this. So this works for all random variables. For continuous x, oh boy. Let's talk about the difference between the CDF at f of b minus f of a. Okay, this is equal to the following four things. This is the probability that A is less than X is less than B, which is equal to the probability that A is less than X, which is less than or equal to B, which is equal to the probability that A is less than or equal to X is less than B. I'm getting bored. Probability that A is less than or equal to X is less than or equal to B. And this is directly related to this issue here. So the equality on any of these bounds doesn't matter if it's strict or not, because the probability at that exact location is exactly 0. Okay. Let's see. The book defines the inverse CDF here. I'm going to sort of skip that. Aha. Okay. So the next step in the book is a discussion of what we would call named random variables. So these are random variables with distributions that come up so often. We gave them a name, and they all have all these sorts of properties and stuff that are well known. So these are things like, your normal, your gamma, your exponential, your binomial, et cetera, et cetera. So before I even say that, we're going to talk about some notation here. So you'll see something like this. So what this notation means is the random variable X, we'll say, has, in this case, CDF, but I'm just going to say distribution F. So this is ridiculous notation because in any other mathematics, the tilde there means approximately, but we use it to denote distribution. So, and since the CDF encodes all the information of a distribution, you'll often see things written like this. So this says random variable X has distribution F, where the distribution is given by that CDF, which is some capital F. Okay, cool. So we'll also use this notation for named random variables. So let's just jump right to one that you've probably seen before. So if I say X tilde n with mu and sigma squared, so this reads X has a, in this case, normal distribution with parameters mu and sigma squared. So these important distributions with names, they often have parameters. And that's because for different values of the parameters, that directly corresponds to a particular PDF and CDF. So let's look at a different example here. Let's look at the binomial distribution for a second. So the binomial distribution has two parameters. So I would write X as distribution binom n comma p. Okay, so this statement here is just a very, very, very succinct way to say the following. So what this means is that X is a random variable with a, in this case, probability mass function, because this is discrete, that looks like this. Let's see. Okay. You might notice that I'm writing this slightly differently than the book's notation. This is one of the very few places where I might deviate. So when I write a probability mass function or density function, and I over here specify the values that get input to it, it's implied that for any other value, the function takes the value 0. But right, so this is shorthand to say that X is a random variable with this probability mass function. and we've left these parameters blank because for different values of the parameter, we get a different probability mass function, but they all share this common form. Oh, and I should note here, P has to be between 0 and 1. Otherwise, this wouldn't be a valid mass function. Okay, so I think that's all I want to say about named distributions. Have a look at all the different ones in the book. I would kind of hope you had seen all of them before. But one note for this class is that any of these distributions, we're not going to calculate quantities like this by hand, right? I want to live in the real world where you have a statistical computing environment. So any of these named distributions, there's going to be a bunch of built-in functions in any legitimate statistical computing environment to calculate these things. So for example, in R, to do binomial distribution calculations, there are 4 functions you would need to know about. And I call those the D, P, Q, and R functions. So in this case, it would be D binom, P binom, Q binom, and R binom. And all of these have arguments. I'm going to skip the first argument to each of these, and I'll talk about that in a second. But then they all have 2 more arguments in this case, so it would be size and prob, and that's true all the way down here. You might be wondering, like, hey, why not just use N and P? Why you got to be so confusing, R? The reason being is that the first argument to R binom is already called N, and I'll say why in a second. So that's one of the keys to all of these statistical learning environments. They're going to have these useful functions, but you just need to match the argument names to the mathematical parameter names. But anyway, so the D function. Well, this is the density. Sorry, can't spell. This is either the density or the mass function. So because we're doing binom here, and basically replace binom with whatever distribution we're talking about, and it'll have different parameters. But so in this case, it's mass function. So you give it the N here, the P here, and like if you put 5 here, so that would be the probability that a binomial random variable takes the value 5 given the parameters, so on and so forth. So the P function is exactly the CDF. The Q function is the quantile function, that is the reverse of the CDF. If you call these on each other, you'll just get the same thing back. And R is for random. So the R is a very useful one for doing simulations because we can generate random variables that have some distribution. That was like the 5-minute overview of how to do probability in R, and I'm really assuming a lot that you know about probability. But if these aren't familiar to you, let's chat in office hours about these. I really love it if everyone, I mean, whether it's in R or some other language, you have the ability to do all of these calculations for basically any of the named distributions in the book. These should be things that are roughly familiar to you. Okay. Let's see here. Do I want to say more in this video? So I'm going to cut this video kind of short and skip a few things in the textbook. So in the textbook, it would go on now to talk about joint distributions. Let's save that for a little later in terms of there's going to be a couple quote unquote simple problems on the homework about that, and we'll touch base there if we need to. but I want to jump to one minor note about some notation we use if we have a lot of random variables. So something that'll be really important is this notion of an IID sample, which stands for independent identically distributed. So sometimes we'll have x, which is now a vector. Call it x1, x2, yada, 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 xn. So we have random variables x1, x2 through xn, and we call that a random vector. And we could say, well, its joint distribution is something like this. So that would be a PDF for that random vector now. And I know I skipped a little bit there. So this IID notion says that this random variable, all the way through this random variable, they are both independent and they all have the same distribution. So we have a notation for that, and it generally looks something like this. We say we have x1, x2, da, 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 xn have distribution f. So this is shorthand notation that says this is a random sample of size n, and each of the random variables is independent, and they all have the same distribution. So we call this a random sample of size n from some distribution f. Or sometimes instead of saying the CDF that it comes from, we could say something like x1, x2, yada, yada, xn are an IID random sample from, say, a Poisson distribution with parameter lambda. So again, this is saying we have n random variables, they're independent, and they all have a Poisson distribution with rate parameter lambda. There's one particular thing to note here that's going to come back much later when we get into inference. When this is the case, I'm going to erase this to make room. This joint PDF here is often a pain to work with unless you have IID random variables. Because if that's the case, I guess I probably skipped a bit about independent random variables. So that's like really the one thing we desperately needed from the part that I skipped. But anyway, this then becomes a product of the individual PDFs. So in this notation here, actually let's make it a little clearer notationally. Right. So, and actually, what I should say is this. So, this is true because of independence, where this is, say, the PDF of random variable x sub I, but they all have the same distribution, which would be in this case the PDF f. Okay. So that was a little bit sloppy. Right. Let's talk to the camera for a second. So I'm going really fast here and being really sloppy because this video and the last one amounted to about, I don't know, half a semester's worth of probability. So I'm fighting this balance of like talk about details but get through it. And then my other internal struggle is, well, we could have just jumped into statistical inference, but I don't want to jump off a cliff and start there, so I wanted to sort of back up and sort of jog your memory about some of this. So there are kind of two things from this chapter that I didn't directly talk about in this video, which were this notion of bivariate distributions and multivariate distributions. I guess the one thing, I mean, you should know about marginal distributions. You should know about conditional distributions. And let's see, what else is missing there? The book mentions multivariate, normal, and the multinomial distribution. Hopefully you've seen both of those. I'm trying to think. I don't think we'll talk about either one too much later on, but those are useful things. And then the thing that I definitely left out was the very last bit of the chapter, which is about transformations of random variables. But there's 2 homework problems on that. So I'm sure if you don't have a good memory of that, you'll come talk to me in office hours. Right. But I was a little bit more interested in just sort of talking about this general idea of a random variable, more from an interpretation standpoint than necessarily a rigorous study with a bunch of exercises and examples in it. So this will not serve as a good example of videos to come, meaning we'll go slower when we hit the real purpose of this course. But I am curious about your thoughts on the me writing things as I do it versus only writing some things and having more prepared statements ahead of time. I have really mixed feelings about that, but if you have strong feelings about it, let me know, and I will adjust accordingly. All right, got to stop rambling now. Do the homework. Come talk to me in office hours. That's more important. As always, if you made it to the end of the video, good job, and I'll see you in the next one.